let me be fancy and write it as vector notation, so you can just add them. Buoyancy is not the force just from the water below you. It's the force from all the fluid around you together. So when you are just in the air, you're looking at a balloon. The balloon has buoyancy on it, and the buoyancy of the balloon is divided by all the force from the air in the bottom, subtracting the air force from the top. You add all the forces that the surrounding fluid is acting on you, and that's buoyancy. When you are in the water, you can still have buoyancy, and then buoyancy is still all the forces that the surrounding fluid is acting on you added together. So it's not just the fluid from below, it's the fluid around you. The force from all the fluid around you added together is buoyancy. Okay? Yeah, okay.
I kind of have a question, like when you, like a more buoyant thing would like float, right? So
yeah.
So then like if it's all the forces added together equals the buoyancy, then wouldn't that be like the opposite? Like wouldn't it sink if there's more forces on you then?
So the sum of these two forces right now will go up or down?
It will like.
It must go up
yeah.
to cancel the gravity goes down. So when you have all the forces added together, a more buoyant thing will give you a result of upward force, and a less buoyant thing will result in a smaller upward force. It's always going to be upward because the pressure up here is always smaller than pressure down here. Because the pressure down here is always bigger, this is smaller, area is the same. So no matter what thing you're looking at, the buoyancy is always going up. It's just that for some buoyant thing, for some object, this total force is smaller than gravity. That is the thing that we're seeing. And for object with buoyancy bigger than gravity, it will float. And I'm going to tell you the exact number we need to use to determine whether the thing will float or not. So we have our buoyancy is force from water plus the force from the air. Let's compute that with pressure. The force from the air is the pressure of the air times the area up on the top. This is P air. This is P water. This is the depth that the thing is sinking down there. So force from the air is pressure times area, same as force from the water is pressure times area. Now, if I write out the equation again, I get the pressure from the, so the force from the water minus the force from the air is mg. So this minus this is mg. Let's take A away, and then we get the change, the difference between its pressure is mg divided by A. Is that too fast? Now, the pressure difference between these 2 points should cancel gravity, but because pressure difference times area is force, you need area. So that's why pressure difference only cancels gravity per area. You can think of it that way. Now, I'm going to do the same trick, multiply by t, or I already done the trick before. I know that this should be rho g t. The difference between the pressure at 2 points will be the density of the fluid times the gravity times this d. So that should be rho GT. So what am I doing here? I get that d should be GG cancels mass, area, and rho. I'm going to move area to the other side and get mass divided by rho. M is the mass of the block. AD is the area of the block times this immersed depth. If you multiply the area of the block times the height of the block, you get the volume of the block. But if you only multiply it by the depth over here, you get the volume of water that the block repulsed when it immersed into the water. So now I get that the repulsed volume is mass of the block divided by the density of water. Let me be more clear. This is density of water, density of water, density of water. Now, if I put it back here, density of water times the volume of water that the block repulsed will be the mass of water that it repulsed. And that should equal to the mass of the block. So what happens when a block is floating on water? The mass of the block equals the mass of the water that is removed. That's the criteria for the block to float on water. Now, what is the maximum amount of volume what's the maximum amount of water that the block can remove, that can repulse? Is the volume of the block itself. When a block is immersed completely into the water, the immersed mass, the repulsed mass, will no longer increase. When you have a heavier object, so let's say this is floating right now. If I push it down, the buoyancy will increase as the repulsed volume increases. But once it's sink completely into the water, the volume that it repulsed can no longer increase. So the criteria for an object to float is that its mass needs to be smaller than the biggest repulsed mass it can give. If you divide by the volume of the block, you get that the criteria for it to float is the density of the block divided is need to be smaller than the density of water. So a buoyant thing means that it has small density, not mass, not volume, but density. Okay? something that is actually important to you guys. Capillary pressure, capillary effect, or capillary force. For a straw, you need to have someone removing the air. You need to have someone sucking the water in a straw in order to rise the water. But if you have a small enough capillary, if you have a small enough tube, it's open on top, no one is sucking it, water can just rise up by itself. No one is sucking water, but water rises up. The reason that this happens is because if you look closer at the interface, the surface of the water has a curvature bend like this. You have an angle divided by theta. This is the angle between the surface of the water and the wall of the tube. You have this bending curvature, and that is the reason you have this difference. For a straw, this surface is pretty flat because you are having a big radius. But when the radius becomes small, this curvature is significant. Why will this curvature give you an upward rising of water? When you look at the surface of water, the particles will be more spread because they are at the surface. Inside the water, the particles will like to stick at a distance that they are comfortable with. They are not too close, not too far. The force between them will be a little bit attractive if they are a little bit too far, and a little bit repulsive if they are a little bit too close. But the distance between particles are basically the distance that they are comfortable with inside the water. But when we go to the surface, there's no water surrounding this particle. It cannot align